a position vector, and I don't know why I have all this white space here, but I'll draw it out. If you go from your origin to any point P, that fixes that vector, and that makes it a position vector. Most vectors that we deal with are free vectors. They float all over the place, but a position vector is fixed to the origin. And we usually denote that as just, if you're going from O to P, then you would just call that vector P. Denote. Did I say donate? You can donate after the class if you thought it was a good one. Tip jar afterwards. Yeah, I don't know how that would go over. Probably not too well. I always get more tips on test day. I don't know why. So we have position vectors of 2 points, M and N, as shown in the diagram there. So then if you want to travel from M to N, how could you do that in terms of just M and N? So we're starting here. We want to end here. But all we can do is travel along M and N. How could we do that? Well, we could go here first. What vector would that be? That would be a negative M. So I can write that Mn would equal a negative M. And then if I traveled from here to here, I would have to add N to it. And so I always like to write it this way, negative M plus N. You'll see in a lot of textbooks that they write it this way, which makes sense, right? But visualizing it, I didn't imagine doing N first and then going minus N. According to my diagram, I visualized going minus M first and then plus N. And I find in this unit particular, if you can visualize how you're going from one place to another, it makes the vector math a lot easier. Okay, so we've got N minus M, or minus M plus N. Considering the same thing, if you had to go from N to M, we went from M to M. Now we're wanting to start here at N and at M. Well, now you would go minus N plus M. I'm going to redraw that picture right now. Now we've got a new point, P. And that point, P, is halfway in between M and N. So what we can imagine is if I wanted to start here at O and get to P, and I can only use paths in terms of M and N, well, can you see, first of all, that you could go from O to P if you went from O to M and then from M to P? That makes sense? Well, O to M is good because we already know that that is M. But we don't know what M to P is yet, other than the fact that it's the midpoint between M and N. So if we went in the direction of M and N but only went halfway, we would stop at P. And since we already know that M to N was minus M plus N, if we simplify this out, distribute the half, m minus a half m will be half m plus half n. So technically, if I draw things nicely, and I'll go back to the original drawing where the lines are all straight. If I can figure out where halfway is here, and I would go half of m, and I figure out half of n, if I join those together, technically I should end perfectly halfway between m and n. So you can get from O to P by going halfway along m and then turning and traveling halfway in the direction of n. So now we can extend this a little bit. Points A, B, and C have position vectors A, B, and C. P is in the midpoint of AB. Q is in the midpoint of BC. Can you find OP and OQ in terms of A, B, and C? And then, oops, I thought there, oh, it's down here. And then find how you would travel from P to Q if you were only allowed to travel in the directions of A, B, and C. So there's OP and OQ. So check it out. If I went halfway along A and halfway along B and join those together, do I end up at P? Not bad. And OQ is half B plus half C, and then P to Q is negative half A plus half C. So if we go to our diagram, that means if I went half of A in the negative direction and half of C in the positive direction, if I started at P and added that, I should end at Q. And sure enough, it matches up pretty nicely. You have negative half C and right here?
No, for A. For the question A. And I have 1/2
Negative B plus A.
negative 1/2, yeah, negative B plus.
So if you're thinking about going from A to B, think about starting at A, you'd have to go backwards along A and then forwards along B.
Oh, so it does matter what order it is.
Yeah, I just thought when you said when it doesn't matter which order, could you write B minus A or minus A plus B? That doesn't matter, but it does matter where you're starting. So if you're going from A to B, you're starting at A and then going to B. Otherwise, it would be BA. So here we have a regular hexagon. So the idea about vectors, and vectors being free vectors, is to realize that A to B is labeled as vector B. Can you see that that's the same as going from E to D? And that if this is a regular hexagon, A to B would also be the same as going from F to O. All of those are parallel and the same length. Did you know when you split up a regular hexagon, you make a bunch of equilateral triangles? All of them are parallel and all of them have the same lengths. So if you want to go from O to B, well, I could get to O to B by going A plus B. I'm probably going to do some of these on the same page so I don't have to flip back and forth from my diagram. Oh, I've got my diagram. No, I don't have my diagram. So B was B to D. If you wanted to go from B to D, start at B, end at D, well, you would have to go this way and then this way. That could be one way of doing it. Now, knowing that this is parallel to this, that will give us a negative A there. And CD is going to be parallel to OB, which we already figured out, but it's going to be in the negative direction of that, minus A plus B. Putting that together, I get negative 2A's plus B. If I think of negative 2A's plus B, and I erase what I have here and say, if I'm starting at B, and I go negative 2A's, that would go once here, once there, and then, oops, I forgot to distribute my negative. This should be a minus sign. If I go negative 2A's and then a negative B, sure enough, I end up at D. And then part C was going from C to F. Well, you could walk yourself all the way around if you'd like, or maybe you think about going 1, 2 in this direction, and each of those will be parallel to B, but in the opposite direction. So you'll just get negative 2B. Yeah, you can do the half arrow or the full arrow. I won't take off marks if you like to do like fancy arrows. Whatever you want. We'll be fine. All right, so we've done. So now we're going to look at vectors and some proportions. So in this question, we've got a parallelogram, so you know that the opposite sides of a parallelogram are parallel and equal length. That's why it's called a parallelogram. Learn something new every day. And we know that O to A is A and O to B is B. And we know that there is a point P, so that the ratio between A to B and B to P is 2 to 1. So what that means is that if this length is 2, this length is 1. Whatever unit we decide, that A to B is double the length of B to P. And Q lies on CB such that C to Q is in that ratio, 1 to 3. So sometimes some of the mistakes that people get in a question like this, if I'm going from C to Q, how far have I gone on my way from C to B? Some people might think it's only you've gone 1/3 of the way, but you've gone 1/4 of the way, right? Because this whole length is 4 if this is 1 unit and that's 3 units. Of course, this isn't to scale, or this doesn't mean that this length is 2 and that length is 3. It's just a proportion. So these might be different units. Okay, so now we've got that sort of idea of what lengths are what. we want to express each of these vectors in terms of A and B. Now, A to B, that one's really straightforward because you can just go negative A and then plus B. But how would we get from A to P? Well, A to P is equal to some number times A to B. What number would I put in front there? 1.5 or 3/2 or 6/4. Yes. Yeah, we can keep doing fractions that are equal to that if we'd like for a very long time, I'm sure. So how do we figure that out? Well, this whole length is 3. And we've gone, A to B is 2 of those, so we have to go 3/2 of those in order to get from A to P. So then we just have to multiply through negative A plus B. So I'd like you to finish the next 4 and then do part B. Or the next 2, sorry, and then part B. So then, once you've done that work from before, to go from Q to P, you can just go from Q to O and then O to P. How would you pronounce that word? Co-op? Coop? Yeah, okay. So there.
If you hyphenate it.
Position vectors, points A, B, and C are as follows. And you want to show that all 3 of those points are collinear. In other words, somewhere in 3-dimensional space, there's point A, point B, and point C, and they are all on the same line. Well, if we figure out the vector from A to B, and we figure out the vector from B to C, now A to B, we can use our position vectors because somewhere in here is also an origin. And so going from A to B, we can use the position vectors that's going to be negative A, and A is 2, negative 1, 1, plus B, and B is 3, 2, negative 1. So we can figure out that A to B is going to be 1, 3, negative 2. B to C would be negative B plus C. And figuring that out, we'll get 3, 9, 8. Did I write those things? No, this was a minus 7, so that'll be negative 6. So how does that help us? I figured out A to B was 1, 3, negative 2. I figured out B to C was 3, 9, negative 6. Yes. A to B is equal to, or 3 A to B's is equal to B to C. So what does that mean? Sure, that's true. If 3 A to B's equals B to C, this means the vectors are parallel. Right? Just one is longer than the other one. But they're going in the same direction. And anytime something's going in the same direction, it's going to be parallel. So one thing we saw earlier is if you take a vector and multiply it by a scalar, so if we took vector A and multiplied it by 3, we get a new vector that's longer but still going in the same direction. And because both of those vectors are parallel, and since they share the point B, these 3 points must be collinear. Does that make sense? Not only are they parallel, parallel in itself wouldn't be enough to show that they are collinear, but since they share this point B, if you're not changing any direction along the way, then you're still going to all 3 points be in the same line. Does that make sense? Yes. So another thing that you could do for this kind of question is you could actually figure out the magnitude of A to B. How long is it from A to B? You could figure out the magnitude of B to C. And then you could figure out the magnitude from A to C. If they're collinear, what would have to happen? The green one plus the red one would have to equal the black one. If they're not collinear, the black one would probably be shorter. It'd probably be quicker to go directly than it would be to stop along the way at another point. So that would be another way that you could show they're collinear. So there's more than one way. I think that the direction way is a shorter way. There's less math involved because you would have to use your distance formula or magnitude formula 3 times in the other method. So let's pick A, B, C, D, and E. A, B, C, D, and E. And say, where would you end up if you went from A to B? Okay. There we go. And then B to C. There we go. Then D to E. Whew. There we go. And then C to D. Where would you end up? You would end up at point E. You started at point A, so then you would go from A to E. Now, I drew it out just to kind of visualize it, but when you're doing your vectors, it doesn't matter which order you do them in. So A to B, B to C, can you see that it would be easier to visualize than going from C to D? And finally, from D to E. Is that an easier way of visualizing A to B, B to C, C to D? That's much easier to see that you would end up at E going in that direction. So as far as simplifying an expression like this, whenever you're adding 2 things, and those numbers are the same, A to B plus B to C, well, that would just be A to C. And C to D plus D to E would be the same as going from C, to E. And A to C plus C to E would be the same as going from A to E. So part B, we've got a bunch of things happening here. Which ones of these can we combine? A to B and B to A are just opposites of each other. They're going to cancel each other out. So with this one and this one, I could combine them to get does that make sense? 2 B to A's? Any other ones that you could see that you could combine that way? We could do 6 C to D's and 2 D to C's. And you see you'd be left with 4 C to D's. And then I'll just write what else is left. So we still have 4 A to C's and 2 D to A's. What would you like to put together next? The first two, the BA and the CD? How do you propose we do that?
Start with 2B there, and
Okay. So you want to put this one and this one together? What would happen?
actually it's probably not possible.
Well, it is possible, but you'd have to break it up a little bit. Because B to A plus A to C gets you B to C. Right? But this one we have 2 of, and this one we have 4 of. So we would be able to put 2 and 2 of them together, but then you'd still be left with some extras left over. It's going to be easier maybe to do these 2 together, because we have 4 of each of those. We can go A to C and then C to D. Can you see that if you started at A, you could get to D 4 times? And then you would still have this 2BA to start with, and then you'd still have this 2DA at the end. See, those will cancel out. So we'll have our 2BA plus, and after these cancel out, 2ADs. Those nicely match up with the middle numbers being A. We have 2 of them, so we end up with 2 BDs in the end. Now I'm going to erase this, and I'm going to say, let's say that's not how you envisioned this. Whoa. Okay, this is going to be intense. I'm going to go around it. As soon as I tap it in the middle, it's going to disappear, Michelle.
That's too easy. That's too easy.
2BD at the end. You ready?
Yeah.
Oh, guess you have to do it faster. Okay. So I'm wondering, would we get the same thing if we saw something else to begin with? Like maybe you were looking at this and you said to yourself, hey, I could put these together. Right? What would that make? 2dB, right? Would that ruin things, or would that not help us? So if I did that first, 2dB plus 4AC plus 4BA plus 6CD plus 2DC. Let's say I did that first. Is there anything else I could put together? Oh, I could put these 2 together, right? What would that make for me? I still have 2dB. This would make plus 4bc plus 6cd. So I'm deliberately trying to do things in a different order here. Maybe now you decide to cancel those out because nothing else, no other things match up nicely with the numbers, right? With the coefficient in front. We've got a dB and a dC, but in order for them to match up in the middle, you'd have to change this to a negative. And so that's a little bit. Yeah, I just said that. Yeah. Okay, but so now maybe you decide, okay, I want to do this. So I've got 2 dB plus 4 BC. And now I put those together and say that's going to be 4 CDs. And then these two could go together, right? And then those would go together. And we end up with the same answer that we had before. Whew. So it wouldn't matter which way you notice how to put them together, just a matter of you applying those same rules over and over again as you put them together. All right, check how you did. Okay, that rectangle I obviously drew not to scale, making the shorter side longer than the longer side. Or what? Okay. Yeah. Anyways, so A plus B is 6, 8. You can think of vector A, and I guess I tried to bold them here. That's probably not a good idea. I'll put the arrowheads on. And then part B, what's the length of OB? Well, that's just a nice A squared plus B squared equals C squared question. Now in part C, OB plus CA just ends up being 2 A's.